Hey, it's snowing outside. So you know what we should do? We should do some math. So welcome to 2.4. Do you like my hair? So this is the last section in Module 2. So let's do it. So we've been talking a lot about quadratic formulas, solving quadratic formulas, things like that. So what does all that mean? So what we're going to talk about is, can I use different methods to solve and graph nonlinear systems? So what happens a lot is you have two different things, functions, or situations, and you want to figure out when they meet. So in this case, this dude, who is a snow jumper or whatever, wants to do some math to figure out if he's going to land on this slope over here. But notice it's not just a normal, just woo, onto a flat surface. He's using a parabolic shape, because that's kind of how things fly through the air. But he's landing on a non-flat line. So we could call this part a line, we could call this part a parabola, and we want to figure out where they meet. So that would be a system of equations. We would have the equation of a parabola. Here's our parabola. And then we would have our line, and we could figure out when those two meet. So that's what we're going to do. So graphically speaking, or just in general, when we're talking about solving linear equations, or in this case, nonlinear quadratic equations or systems, so what does that mean? Like, how do you solve them? What does it mean? But what it basically means is when the two lines that you're dealing with, or line and functions, whatever, when do they intersect? And as I mentioned earlier, that can help us solve a lot of real-world type kind of problems. So for example, this isn't a real world problem, but it's our first one. So we've got a linear line, it's very liney in blue here, and solving the solution of a system of equations of this line and this circle would be figuring out where these 2 points intersect. And so we can do that graphically like you see here, or we can also do it algebraically. And that's what we're eventually going to figure out. So a real-world example of a linear quadratic system is shown. The coverage area of a cell phone tower can be represented using a circle with the cell phone tower at the center. The line representing a road that passes through the area. The road intersects the edge of the cell phone tower's coverage area at 2 points. These 2 points. So if you've ever seen on like all those cop movies, and they're like tracking somebody based on the cell phone tower that they're at, I mean, they've got a computer that's basically doing this problem just a lot faster than you and I can. But anyway, we can look at this different situation where we have a parabola and we have a straight line. So the graph shows a linear quadratic system, line, whatever that is, parabola, which represented by the equation y equals 2. So that is our line. So how many points of intersection does the system have? We can look at it, and it clearly has only just one. So we can say 1. Yay. So if we vertically translate the line up 3 units, so we're moving this line up 3 units, 2, 3, 4, 5. So it would be this line right up here. How many solutions would we have? Well, it would now cross the parabola in 2 places, so we would have 2 solutions. So remember, algebraically, this is why we get a plus and a minus anytime we solve our quadratic formulas. By the way, our solving quadratic formulas is basically doing the same thing, except we are defaulting to y equals 0, aka the x-axis. So, I'm not going to draw that picture. Y'all are fine. So select the arrow to show the correct graph. So the graph would look something like this, or it would look exactly like this. Again, we've got two spots here and here where it crosses. So let's see here, vertically translate the original line, y equals 2, down 4 units. So it starts here, down 4 units, it would be down here. And there would then be 0 solutions, or 0 real solutions if we wanted to say that. So that would look something like this. So we've got our parabola here and our line right here. So let's see, what do you recall about a line that is tangent to a circle? How many solutions are possible in a system where a line is tangent to a circle? So by definition, a tangent to a circle is a circle with just that line coming through and touching the circle in one spot. So a line that is tangent to a circle intersects a circle at exactly one point. There is one solution possible in a system where a line is tangent to a circle. This is because there's only one point of intersection. Think about how many ways the graph of a linear function can intersect the graph of a circle. How many solutions can a system composed of a line and a circle have? It could potentially, I was going to draw a picture, but they did it way better than me. So you can potentially have your line outside of your circle, not touching at all, in which case you'd have no solutions. You might have your line touching the circle, but not going through the circle. You'd have one solution. Or you might have the line going through the circle, and you would have two solutions. So up here, you would have no solution, one solution, or two solutions. You cannot possibly have three or more solutions if you're dealing with just a line and a circle. There are other equations out there that you might have more than two solutions, but we're not dealing with those today. How does the possible number of solutions for a system of linear equations and a circle compare to the system with a linear equation and a parabola? So it's the same number. A circle, you can have 0, 1, and 2. A parabola, you can have 0, 1, and 2 as well. And is it possible for a linear quadratic system to have infinitely many solutions? No. The most you can have, again, if you have a line and a quadratic system, are 2. So no, there cannot be infinitely many solutions because the graph of quadratic equation is a parabola, and any line can intersect the parabola in, at most, 2 points. Now, again, if you had two different functions and they were both parabolas, then yeah, maybe if they were the same parabola. But we're talking about a line and a parabola. Okay, so let's try one out. So we've got a linear quadratic system by graphing. So in this case, it's a linear circle-ish system, but by quadratic, they're just referring to like x squared and y squared. So you can express a circle that way. Anyway, so it says solve the system of equations by graphing. 3x plus 4y equals 25, and x squared plus y squared equals 25. So if we were going to graph this top one, so it said solve by graphing, this equation that they have here is not that helpful yet. So you want to put that equation into something that is a little bit more helpful, and hopefully you are remembering this thing called y equals mx plus b. That is your slope-intercept form of a line. So if we put it into that form, then that will actually tell us something a little bit more. So we're just going to algebra it until we have y equals. Okay? So I'm going to move the 3 over to the other side. So I'm going to have 4y equals 25 minus 3x. We're going to divide both sides by 4. So we're going to have y equals 25 minus 3x over 4, which you can then turn into, let's see here, y equals 25 divided by 4 minus 3 over 4x. So I just divided it out, that's all. So now we've got it in y equals mx plus b. We've got our slope. Ooh, I can change colors. We've got our slope. We've got our y-intercept. Yeah, our y-intercept. And so we can graph that, right? So there we go. So, and also if you don't remember, x squared plus y squared equals the radius squared of a circle. So that's how we would graph that. The radius squared, we take the square root of that. Square root of that is 5. So the radius of our circle is 5. And you'll notice that they connect in just that one point right there. So how many solutions will this system have? One solution. There's only one line. That doesn't make sense. One solution, there's one point of intersection. So find the solution by identifying the point of intersection, 3, 4. So they're just looking here, and they look at this little point right there, and it comes down. That's 3, that's 4. Boom! We have our answer. So just to make sure, they plugged the 3 4s back into both equations to make sure that it worked. So again, we're picking 3, 4. Our initial equation, 3x plus 4y equals 25. We shove the 3, we shove the 4 in there, and we make sure that it does in fact equal 25. And then we shove the 3 and 4 into the second one, make sure that that this equation is a true statement, and then we're good to go. So they do all of that right there. So again, especially if you're looking from a graph, you will definitely want to check your work. So why must the solution satisfy both equations? The solution must be a point that lies on the line and on the circle. If the solution satisfies only one of the two equations, then it is not a solution of the system because it is on only one of the graphs. Okay, that was kind of dumb, but whatever. So now let's actually do it algebraically. So you can solve nonlinear systems of equations algebraically using elimination as a solution strategy. Add or subtract, blah, 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 blah. So this is a way to solve these things called elimination. Some other ways that you can solve systems of equations is by substitution. You have two equations, two variables. You use one equation to make a variable equals whatever, then you plug into the other one. Or you can use this method called elimination. Again, if you don't remember anything about these things, you might want to review a little bit. There's no shame in Googling solving system of equations using elimination. That might help. But, so for here, solve the following system algebraically. So we've got 2x minus y equals 9, and this weirdly spaced out, y equals 3, blah, 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 all that stuff. So they weirdly spaced it out here intentionally because when you are going to when you're going to solve a system by using the process of elimination, you want to line your variables up. So in this case, they're going to eliminate their y, and I assume that we're going to eventually solve for x and something like that. So you've got 2x minus y, and you got y equals all this stuff. So because we've got a negative y and a y, all we have to do is add those equations together. So again, this is like 2.2 or something like that. We're just going to combine like terms if we add both of those things together. So they put them all, they lined everything up. 2x plus nothing is 2x. Negative y plus y is 0. Nothing is here, so we're just going to bring all that stuff down. We've got a -1, we've got a 9. We combine like terms, we have an 8. So now we have 2x equals 3 times x plus 4 quantity squared plus 8. Hopefully, that looks like something maybe we might be able to solve. So should you add or subtract to eliminate y? In this case, you should add. Since y are different, to eliminate them, you would need to add. You can always subtract, but just whenever you do subtract, make sure you distribute that negative sign to the whole equation, lest you make a mistake like I do all the time. So, okay, solve the new equation. So here is our original equation. There it is. So we're going to shove everything on the over onto the right. So minus both sides 2x. So here we are. So then from there, they are squaring this thing out. That's what this part is. So then we got to distribute this 3 in. And that's where we get this part. And then after that, we're going to combine like terms. And we have this. So this is solvable, right? All we have to do is plug and chug and use the quadratic formula. Unfortunately, that's probably the only thing that's going to work because those numbers just look crazy. So, but this is just the quadratic formula. A, B, C. Shove it in the quadratic formula, simplify, and now we're looking at this. Okay? So, again, we just threw it into the quadratic formula, and we'll practice that, don't you worry. But that's all they did. So then what does the value of x equals blah, 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 blah tell you about the solution to the system? The discriminant is negative, so there are no real solutions to this system. So that means we've got a line, and we've got a parabola, and they do not cross each other. There's our graph. So they do not cross each other. Does this graph verify your result? Yes. It verifies my solution. There is no solution. Thanks. So we solved the system using elimination. Sometimes that doesn't work. So for example, here we have a real world problem with a router broadcasting a Wi-Fi signal. Note our Wi-Fi signal here in the classroom is outside of the room. What sense does that make? But a router broadcasts a Wi-Fi signal in equal distance in every direction. The range of the broadcast of the router that can reach up to 50 feet can be modeled by the equation x squared plus y squared equals 2500. Carl walks across the yard on a path modeled by an equation y equals 2x plus 35. At what points will Carl enter and leave the broadcast signal? Because everybody needs to know when they're going to have Wi-Fi and when they're not. So here, we've got an x squared plus y squared, and we've got a y equals 2x. So elimination would not be easy. It would be possible. We could square root some stuff, but it would not be easy, and it would probably be more work than it's worth. So the good old-fashioned traditional way of solving this would be by using the method of substitution. So this is where we have y equals 2x plus 35. We're just going to shove this y into this other equation up here. So if we take, where's my pencil? Here we go. So if we take this and we add it into, or we plug it into our y there, here's our y, and notice how it is now squared. Okay, so we algebra this part out. So 2 times 2x is 4x squared. 2 times 35, and then multiplied by 2 is going to be our 140x. And then 35 times 35 is going to be right there. So I'm breezing through this part because this is just simply working that part. Obviously, when I do this stuff on the board, I have to do way more steps than this, but that's because I'm a visual person and whatever. So then we need this to equal 0 so that we can use our quadratic formula, or maybe it's factorable, I don't know. So we're going to move our 25 over to the left, and so here we are, we have this part right here. Why do you write the equation in standard form? Because I can, in order to use the quadratic formula. Good thinking. So again, we're just going to use the quadratic formula at this point. Negative b plus or minus b squared minus 4ac all over 2a. Plug everything in. Algebra, that's this part right here. Go gadget math. And then we're going to have x is approximately equal to 7.24 and x equals negative 35.24. So here's our exact answer. Notice we have a plus or minus. Don't forget, that gives us 2 answers. And so, especially because this is a real-world kind of situation, they just threw this. I mean, they probably literally just threw this stuff into their calculator, and that's how they came up with these negative numbers. You can also do this all by hand, but either way, it's just working on a calculator. Be careful when you do this, when you enter this in your calculator. Make sure that you are appropriately using parentheses to ensure that this 10 is divided by all of this. So you would put this part in parentheses and then divide it by 10. But I encourage you to do that on your calculator. Make sure you get the same answer. If you don't, we need to talk about how to use your calculator. So now we have 2 points for x. So now we can use those points, plug them into either of the equations. It doesn't actually matter. I would always pick the easier one, but hey, that's just me. And then again, since we're dealing with decimals, you're probably going to just have to use your calculator and poof. So all they did is they plugged the 7.25 into y equals 2x plus 35. So then they wanted to find the other one. So they're going to substitute. There we go. Negative 35.25. Again, we're going to shove that into our equation. And we're just going to solve it. And we're going to get this part right here. So this part is all just your quote-unquote normal math. I put that in quotes because I've forgotten it too, so it happens. But then from here, we now have 2 points of intersection. The solutions are approximately 7.24. Why it's up there, I don't know. 49.49, that's a point, and negative 35 and negative 35. So why are the solutions in the system approximate? Solutions given are approximate because an irrational number was approximated when solving for x. Can the exact solutions be given? Yes, exact solutions could be given if the irrational numbers were kept instead of approximated. So when you're dealing with real-world situations, though, I don't remember if I mentioned this in class, but if you hand an engineer or somebody like, hey, go square root of 3 times over there, no, you're going to have to put that into a decimal point, or your engineer is going to look at you like you're crazy. So that being said, we're done, at least for here. So everything totally makes sense, right? Yeah, we'll see. So try out the check on learning. Again, this is solving systems of equations. And if you need to kind of step back and review some of that Algebra 1 stuff, just Google in systems of equations. Khan Academy is an amazing thing. Or you can always ask me, and I will happily talk more math with you. So check on learning. You got it.